Hey, it's Mr. Shrum, and this is part 2 of the kinetic and potential energy tutorial walkthrough. And last time we looked at potential energy and kinetic energy. I explained that potential energy depends on the position of an object, and the kinetic energy deals with the motion. Objects in motion. So position, potential versus kinetic motion energy. And now we're going to look at how to solve those problems in the mastery tests. And this summarizes what we've learned so far, basically what I just said. At rest, an object has a certain amount of stored potential energy. But when it's not moving, it has no kinetic energy. That only has kinetic energy when an object is in motion. Back to the rubber band example, a stretched rubber band, has potential energy to bring it back to the original position. When you release it, you set it in motion so that it has kinetic energy as it moves from stretched to slack position. In other words, its potential energy is converted to kinetic energy. That stored, stretched energy is converted into motion, kinetic energy. The same is true when you hold a stone above a sheet of glass. It has potential energy. It could potentially fall on that glass. As soon as you drop it, the potential energy starts to convert into kinetic energy. Its potential energy as it's held above the glass is equal to its kinetic energy right before it touches the glass. You could say that kinetic energy is energy in action, while potential energy is hypothetical energy, energy that could do something, but it's not in action. The law of conservation of energy. The law of conservation of energy states that energy can be neither created nor destroyed. It can change from one form to another. The total amount of energy in the universe remains constant. So all of the energy, everything that is here has the same amount of energy at all times. It just changes from one form to another. The potential energy of an object starts getting converted into kinetic energy when it moves from a position of rest. Eventually, the potential energy is completely converted into that kinetic motion energy. At any point, the sum of the kinetic and potential energy of a body or object remains the same. It's best to look at an example. So imagine that stone held above the glass sheet. When the stone is raised above the glass, it has potential energy, but no kinetic energy. At rest, all of the energy is potential. When you release the stone, the potential energy starts decreasing and being converted into kinetic energy as it gets faster and faster. Finally, at the point of contact with the glass, the velocity of the stone is at its maximum, and the kinetic energy is at its maximum, and the potential energy is at 0. It's completely converted into kinetic energy. And at any given points on that path, when you drop the stone to when it hits the glass, if you add up the potential energy and the kinetic energy of the stone, it will remain the same, right? It's just being converted. And this has a lesson activity. But this slide has an actual calculation. Tiffany is swinging, and we'll define the 0 potential energy position to be the ground, not the lowest position of the swing. So Tiffany's kinetic energy at the position where the swing is directly hanging down, not swinging one way or the other, that energy is 196 joules. Joules is the SI unit of measurement for energy. And at the mean position, the swing is 0.5 meters above the ground. The extreme position, when the swing is at its furthest point forward or backward, the swing is 1 meter above the ground. The combined mass of Tiffany and the swing is 40 kilograms. What is the total energy at both positions? If we look at the solution, we calculate the potential energy first when it's just hanging down. The potential energy is mgh. We know that the mass is 40 kilograms. G is the acceleration due to gravity, which is 9.8 meters per second squared, times the height. And at the mean position, the height is 0.5 meters above the ground. And that equals 196 joules. Once she swings up to the maximum point, the height changes, but the mass and the acceleration due to gravity stay the same. M is still 40 kilograms. G is still 9.8 meters per second squared, but the height is now 1 meter off the ground. And if you multiply that together, you get 392 joules. The velocity of the swing becomes 0 at the extremes. So she stops moving at a split second when she reaches the furthest point on the swing, and then she changes direction. She goes backwards. So to find the total energy, you're adding up the potential energy and the kinetic energy at the mean point when the swing is lying directly below the bar. So we're told the kinetic energy at the mean position is 196 joules. We calculated the potential energy at that same point, and that is 196 joules. So to find the total energy, you add the potential energy, which is 196, and the kinetic energy, which is 196 as well. And 196 plus 196 is 392 joules. At the extreme position, the total energy is the same calculation, but there is no kinetic energy because you stop moving at the extreme position furthest from the swing. We calculate the potential energy at the extreme. It is 392 plus 0 equals 392. Notice that the total energy is 392 at both points. But the thing that has changed is the potential energy and kinetic energy. This is the equation for potential energy, mgh. The kinetic energy is 1/2 mass times velocity squared. And the total energy is the sum. You're just adding the potential energy and kinetic energy at any point along the problem. So it starts out, this stone, it's a 2 kilogram stone held 1 meter above the ground and released. Its initial velocity is 0. So it's starting from rest. And its final velocity before it hits the ground is 4.42 meters per second. So we're going to add the potential energy and kinetic energy at 3 points, where it starts at the ground and then halfway between the ground and when you drop it. And at that halfway point, the velocity is 3.13 meters per second. So first, let's take it at the initial point. So when you're dropping the stone, it's starting from rest, so it's not moving. There is zero kinetic energy. To calculate the potential energy, you multiply m times g times h. The m is 2 kilograms. The g is 9.8 meters per second squared. And the height is 1 meter. So 2 times 9.8 times 1 equals 19.6 joules. 19.6 plus 0 equals 19.6 joules of total energy. So that's when you hold it in your hand at the ground. Once the rock hits the ground, the potential energy is 0 because the height is 0. So that cancels out. The kinetic energy is 1/2 times the mass, which is 2 kilograms, times the velocity, the final velocity, which is 4.42 meters per second squared. And if you multiply all that out, you get 19.6 joules. 0 plus 19.6 equals the total energy of 19.6 joules. So at the initial point, it's all potential. At the ground, it's all kinetic. And then if you go to a point halfway down, like right here, it's between where you leave it and then before it hits the ground, you have to multiply the potential energy and kinetic energy. So you have mgh, which is 2 kilograms, times g, 9.8, times the height midway between when you leave it and the ground. So if you hold it 1 meter above the ground, halfway down would be 0.5 meters above the ground. So you have 2 times 9.8 times 0.5, and that is 9.8 joules of potential energy. Kinetic energy is 1/2 times the mass, kilograms, times the velocity halfway down, which is 3.13 meters per second squared. And if you multiply that out, you get 9.8 joules of kinetic energy. And if you add potential and kinetic energy, you have 9.8 plus 9.8, and you get 19.6 joules of total energy. So at 3 points, the total energy remains the same, but the potential energy and the kinetic energy is changing depending on where it is, the position, and how fast it's dropping to the ground. So here you have a few questions. It says a 20 kilogram anvil is held at a height of 3 meters above the ground. What is the potential energy of the anvil at that point? Enter the variable symbol for the quantity you need to find. So we need to find PE, potential energy. From this point, you have to go to the correct energy equation for potential energy. And that is potential energy equals mass times the acceleration due to gravity times the height. Now, substitute the numerical values into the equation for all known variables. Use your keyboard and keypad to enter your answer. So the mass is 20 kilograms times G, which is 9.8 meters per second squared times the height, 3 meters above the ground. Enter the variable symbol for the quantity you need to find. We're looking for the kinetic energy, which is Ke. Oh, whoops. Ke, and click done. Moving on to the next question, or well, the next part. A 10-kilogram bird is flying at a velocity of 5 meters per second. Find its kinetic energy at that point. So click on the library, look under energy and momentum, and look for Ke, 1/2 times mass times velocity squared. That is the correct general equation. And now we're going to use this and just plug in the numbers we need. The mass, it's a 10-kilogram bird, and the velocity is 5 meters per second squared. And that's all you need to do for that. So in summary, energy is the capacity of an object to do work. And that energy can be kinetic, motion energy, and potential, stored energy. Potential energy is the energy of a stationary object due to its position or location. The different types include gravitational potential energy, mechanical potential energy, and electrical and magnetic forces that have some type of potential energy as well. Gravitational potential energy is the energy stored in an object as a result of its vertical position above the ground. And to calculate that is mgh, mass times the acceleration due to gravity times height. And g is always 9.8 meters per second squared in this class, unless told otherwise. Mechanical potential energy is the energy stored in an object as a result of the object stretching or compressing, like a rubber band or a spring. Potential energy from field forces like electrical, magnetic, or nuclear forces are results from the stored energy of an object in those force fields. And we won't be talking about that so much in this lesson, but further on down your physical science journey, we'll talk about that. Kinetic energy is the energy that an object has due to its motion. The kinetic energy of an object depends on its mass and velocity. The equation for that is 1/2 times mass times velocity squared. Remember that an object at rest has 0 kinetic energy because it's not moving. The potential energy of an object at rest starts converting to kinetic energy as soon as the object starts to move. Change in the energy of an object is governed by the law of conservation of energy. And that law states that energy is neither created nor destroyed. It can change from one form to another. In a closed system, the total amount of energy is constant. So for the example, in these problems we're working, the sum of the potential energy and kinetic energy is constant. And that's it for the rest of that tutorial walkthrough. I hope you learned something about kinetic and potential energy, and I will work through the mastery test questions in another video. But until then, have a great day, great weekend, great week, whenever you watch this, and I will see you guys later. Bye.